Thank you very much. This is the presentation for our work, Property Inference from Poisoning. I'm Saeed Mahloujifar from Princeton University, and this is a joint work with Esha, Ghosh, and Malicious from Microsoft Research. In privacy-preserving machine learning, we often deal with a setting where there are multiple data providers who want to train a joint model on the union of their data by interacting with each other and potentially a central learner. They need this whole process to be privacy-preserving, meaning that an adversary who can observe the steps of computation as well as the final trained model cannot infer sensitive information about the datasets of these parties. This setting is usually referred to as honest or semi-honest privacy, where the adversary is only an observer. There is a stronger notion of privacy referred to as malicious privacy, where the adversary can collude with some of the data providers and make them deviate from the protocol with the goal of inferring more sensitive information about the data of other data providers. What are the solutions that we have in such scenarios? Well, we have strong cryptographic tools that enable us to eliminate the concern about the information leakage from computation. Even in the malicious privacy regime, using the right cryptographic primitive enables us to consider the whole training as a black box that just outputs the model. The only cost that we have to pay to upgrade to malicious privacy is to use stronger crypto primitives that are usually less efficient. Although this is fantastic, we still have another source of leakage that we have to worry about, which is the leakage from the trained model. To measure this leakage, there are works that that propose techniques to evaluate the leakage of these trained models, but most of them are only designed for the honest setting. And the motivating question in our work is to understand if there is a gap between honest and malicious privacy in terms of the leakage from these models. The leakage model that we consider is property inference, where we have a data set consisting of a bunch of features and a label, and we have this training algorithm that outputs some model. This data set supposedly has a sensitive property that the attacker tries to infer some statistics about. For example, imagine this data set is an email data set, and the adversary wants to find out how many emails in this data set have a certain word in it. Other than this statistics being sensitive, I'm going to give you two other reasons to convince you that this is an important threat model to consider. First of all, it's equivalent to the statistical query model of Nissim et al., where they show that if you make enough of these queries, you can actually reconstruct the whole data set. The other reason is this is a generalization of the well-studied membership inference attack, where the adversary wants to infer whether a specific instance is a training set or not. So if you design your property carefully, this property inference attack will render into a membership inference attack. In this work, we look at an extension of this threat model and leakage to make it work in the malicious setting. So what we consider is an adversary who additional to observing the model, it can also poison the training set by injecting some malicious inputs. And we ask if these kind of poisoning attacks can help property inference leakage. In this work, we propose a new attack for property inference that uses poisoning. And in summary, this figure shows our result, where this x-axis is the poison ratio, and y-axis is the attack accuracy. And as you see, poisoning can significantly increase the leakage. I'm going to describe in the next slides what we mean by attack accuracy, how our attack works, and And finally, some details about the experiments. To talk about attack accuracy, we have to formally define what we mean here. So we define this as a security game between a challenger and an adversary. So our security game has multiple parameters, two distributions, D and D prime. We have a property F, which is the sensitive property the adversary wants to attack, and it has the condition that the first distribution has more probability for that property versus the other distribution. And we also have this learning algorithm. The security game goes as follows. The first step, adversary first selects a poison set and sends it to the challenger. The challenger will randomly select a bit B, and based on that bit, selects one of these two distributions, D and D prime, and samples a data set from the distribution. And after that, it will just calculate the union of the poison set and the sample, train a model, and now the adversary gets to query this model and get the result back, and it can repeat this process as many times in an adaptive way. Finally, the adversary is outputting a bit B prime, and the success of the adversary is measured by the probability that B is equal to B prime. And we refer to this as accuracy of the adversary. Our adversarial model has some assumptions. We assume the adversary knows the distributions D and D prime, and we assume the adversary knows the learning algorithm L. The data distribution assumption might sound very strong to some people, but we have settings that relax this assumption, and in our experiments we show that sampling from a proxy distribution can have the same effect. I'm not going to talk about that setting here, but we have more experiments in the paper for relaxing this assumption. We also assume that the adversary has access to the model, both in the black box way. The white box setting is also well defined, but we are interested in the black box setting where the adversary only queries the model and it only gets the label back. We don't even give it the confidence. All right, so the setting is, now the setting is clear. Let's see how our attack works. Our attack has two steps, as we discussed in the security game. The first step is to do the poisoning. The poisoning strategy is actually very simple. So assume this is our original data set. The way the poisoner, the adversary poisons the data set is to sample a number of examples conditioned on the sensitive property being equal to 1. And it sets the label equal to 1 as well. So it basically creates this fake correlation between the sensitive property and the label. And now, how do we do the inference? This is also very standard using the shadow model training technique of Shukri et al. So basically, the adversary, because so far it knows the poison data and it knows the victim model, what it does, it first samples a bunch of data sets, referred to as shadow data sets, according to D and D prime. It trains a model on the union of these data sets and the poison set to get models, and then it labels them according to whether they're sampled from D or D prime. So at the end, we get this data set that we can do machine learning on again and train an attack model that is going to be used to infer whether M was trained on D or D prime. So this is the full description of the attack, except that I didn't tell you how we represent each of these models. We don't have access, white box access, but what we do is we just basically query a number of points on these models and use that as the representation of these models. So why should this attack work? The high-level idea behind the success of the attack is that the poisoning creates a disparate effect on the Bayes optimal rule underlying these data. What do I mean by that? So consider these two cases where we have these two data sets that of individual people, and the property of interest is gender. We want to find out what's the fraction of male people in the data set. And assume that label is actually the education level of the individuals. After poisoning, the data set looks like something like this. Now, if you think about it, if you think about the probability of education being high, condition of this property of interest, which is male, so the probability of education being high for condition on being a male is much higher in the case that in the D prime case where the original probability of having males is smaller. This is because the Poisson rule, the fake correlation created by adversary, is more dominant in this case. And this means that if you want to achieve a high accuracy classifier on this data set, you have to actually have many points that the prediction is different on the left case versus right case. And the adversary is going to find these points and use them to find out which data set was used or which distribution was used. We make this into a theorem, this intuition, and prove the following result. So basically, it says that if you have a learning algorithm that achieves high accuracy, it's hard to defend against these attacks. Basically, if you output an accuracy, a classifier with error less than epsilon with probability more than 1 minus delta, then with O epsilon poisoning, you can achieve 1 minus 2 delta accuracy on any sensitive Boolean feature. Now let's see a little bit of details about our experiments. So we do multiple data sets, census income data, Enron email data set, and a Celeb A data set, which is basically images of faces. And we consider multiple features for these data sets. One of the specific features that we have is random feature, where we add this particular random feature that is independent of all other features on the label. This is particularly interesting because it doesn't have any correlation, and if you don't do poisoning, you don't have to leak this property at all. We also consider other properties. For example, in Enron data, we consider this email sentiment, where we label each email based on positive or negative sentiment in the email, and the adversary wants to find out how many emails have positive sentiments. And this is again the same summary of our results. So I wanted to just point out a few other things. We do experiments on a range of architectures, from logistic regression to ResNet 50. And they all have the same effect. They're always successful, which is in line with what we expect from our theoretical results. And I want to also point out some of our experiments we did with DP-SGD as a potential defense mechanism. We were interested in DP-SGD as a twofold defense, because DP-SGD is proposed as a privacy-preserving scheme. We don't expect it to mitigate property inference attacks because it's not designed for that, but it still will be interesting to see this. And also, it could be seen as a defense against data poisoning because it has some robustness properties. What we observe is that at the end, DP-SGD is actually not a good defense against this attack. Even with epsilon less than 1, we can still get 91% attack accuracy. And only when the classification accuracy drops to lower numbers is when we see some degradation in the attack accuracy, which is expected from our theory. So to summarize, in this work, we show that poisoning attacks can significantly increase the information leakage in machine learning. And these malicious strategies should be considered for information leakage in scenarios where malicious privacy is the right threat model to consider. For example, whenever we use MPC with malicious security, it also makes sense to look at these malicious strategies for model leakage. And finally, I want to point out to this interesting synergy between robustness and privacy research that can lead to interesting future directions. Thank you very much.
Thank you. Thank you, Saeed. Anyone has any questions, please come to the mic, and maybe just introduce yourself, your name, and where you're visiting from.
So, Isa Khalil from Qatar Computing Research Institute. My question about the practicality of the attack and the cost of launching the attack, because it seems that the attacker has to have full access to the data sets and to the model, and at the same time he can poison the data set, and he has to train all these models in order to be able to achieve the attack.
Yeah, so we have justification for all the points that you mentioned. For poisoning, it's reasonable in multi-party settings because data is coming from multiple sources. So you can imagine some of them go malicious. Access to the model is reasonable again because the model is usually, you have all these model as a service models that you have that you can use, the adversary can use. And the running time of attack is also reasonable. We did experiments on my computer, basically. Yeah, so there are questions about practicality, but these attacks, we don't design them to be practical. We just want to measure, basically, the information leakage. Although they're still practical, in my opinion, but it's mostly used to measure the leakage and not to implement it as an attack anywhere. But there might be adversaries that try to make these even faster, use other, instead of using the actual data set, they use proxy distributions. So there are ways to relax all those assumptions. I hope that answers your question.
Great.
I have a quick clarification on this understanding the data. By the way, Murat Kantarcıoğlu, University of Texas at Dallas. So you assume the data, you know something about data distribution D. Does it involve knowledge about the sensitive attribute as well?
No, if it does, it wouldn't be interesting.
So
right?
you know all the other attributes and their distribution except the sensitive data.
So basically, you know the conditional distributions based on that property. So you know the distribution of males and you know the distribution of females, for example. You don't know with what ratio they're combined. But again, as I said, this is a big assumption that we can relax in some of our experiments using some proxy distribution. So we can relax this condition.
So I was just trying to understand by your assumption how much sensitive things you can infer by default anyway. So even if you don't launch the attack, by what you assume to know, can you infer something sensitive anyway?
No. So this sensitive feature that we are interested in, we cannot infer at all based on this assumption. So this assumption does not imply any attack by default.
Thank you. We have maybe time for one quick question. Okay, maybe I have a question. So when you showed the epsilon, I was just wondering if you were to do like a group privacy, do they correspond at all for like if you were to do group DP?
So because this is a constant fraction, group privacy will have a huge hit. So yeah, I don't think it will lead to any interesting upper bounds on the success of these attacks.
Great. Thank you. Let's thank Saeed once more.